Hi, Fred here. Let's talk about signal integrity, the science of keeping electronic signals clear and reliable. Every text, video, or app relies on billions of tiny electrical signals, our device's digital language. Without good signal integrity, devices crash, freeze, or miscommunicate. Let's dive into how engineers keep those signals clean. Early electronics were slow and simple, but today's tech demands lightning-fast signals through dense circuits. As speeds increase, signals face more noise and interference, like smoke signals in a windstorm. Engineers now design intricate circuit boards and use advanced testing to keep signals strong. Signal integrity is crucial for the performance and reliability of every modern device. Electronics use analog signal, smooth and continuous, and digital signals on-off pulses, the ones and zeros. Digital simplicity allows for accurate, reliable communication, but even these pulses are affected by resistance and capacitance. Signal integrity ensures these digital lifelines arrive clean and ready for action. Digital signals often take the form of square waves. Rapid voltage flips between on and off. These waves are built from many frequencies. If any are lost or distorted, the signal degrades. Understanding and preserving these frequencies is key to maintaining signal integrity. Modern devices push signals to extreme speeds, making them sensitive to imperfections. Fast signals have short rise times, acting like high-frequency waves, easily disrupted by circuit flaws. The faster we go, the more challenging it is to keep signals sharp and undistorted. Signals travel through channels, circuit traces, connectors, cables, each with its own quirks. Real-world channels have imperfections causing impedance mismatches like potholes for signals. These mismatches can reflect, distort, or weaken signals, threatening integrity. In digital electronics, signal shape matters. Distortion leads to errors, crashes, and glitches. As devices get faster and more complex, maintaining signal integrity is like building a stronger foundation for a taller skyscraper. Next, let's see how engineers tackle real-world signal challenges on circuit boards. Impedance. Mismatches on circuit boards cause signal reflections, like echoes in a hall. Every bin, component, or via can disrupt the signal's path, distorting square waves and causing ringing. Engineers fight back with careful design, simulations, and materials to keep signals flowing smoothly. High frequencies, crucial for sharp digital edges, are most vulnerable to loss as they travel. Effects like the skin effect and dielectric absorption weaken these frequencies, blurring signals. Engineers use wider traces and low-loss materials to preserve high-frequency integrity. Crosstalk happens when signals on nearby traces interfere, like voices overlapping in a crowded room. Fast, closely packed signals make crosstalk worse, corrupting data. Engineers space traces apart, use shielding, and carefully route signals to minimize interference. So far, we've been focusing on specific signal integrity challenges, like reflections, attenuation, and crosstalk. But lurking beneath these specific issues is a more general faux noise. Think of noise as the static on a radio station, the fuzz on a TV screen, or the hiss you hear when you crank up the volume on an amplifier. It's the unwanted random electrical energy that finds its way into our signals, masking the information we're trying to transmit. Noise can come from a variety of sources, both internal and external to our electronic devices. Internally, we have things like thermal noise, generated by the random motion of electrons within conductors, and switching noise caused by the rapid on and off transitions of transistors. Externally, we have everything from radio waves to electromagnetic interference from nearby devices, all vying for space in the electromagnetic spectrum. Just like that crowded room full of conversations, the more noise there is, the harder it is for our signals to stand out and be heard. Engineers use a multi-pronged approach to combat noise, from filtering out unwanted frequencies to shielding sensitive components from external interference. They also pay close attention to grounding techniques, providing low impedance paths for stray currents to flow away from sensitive circuits, like creating designated quiet zones within that noisy room. So far, we've explored how signal reflections, losses, crosstalk, and noise can distort the shape and strength of our digital signals. But there's another equally insidious threat to signal integrity that messes with a fundamental aspect of digital communication: timing. Think of it this way. Imagine you're having a phone conversation, but every few words arrive a fraction of a second too early or too late. Even if the words themselves are clear, that timing jitter would make it incredibly difficult to follow the conversation. In the digital world, this timing precision is paramount. Remember those square waves, diligently switching between ones and zeros. The receiver on the other end relies on those transitions happening at precise intervals to accurately interpret the incoming data stream. It's like a perfectly synchronized dance routine. Every step, every beat has to be timed perfectly for the overall performance to shine. Even the slightest deviation from that perfect timing, those tiny fluctuations in the arrival time of our digital pulses, can introduce errors and wreak havoc on our digital systems. This timing uncertainty, those seemingly insignificant deviations from perfection, is what we call jitter. It's the bane of high-speed digital designers, a constant source of headaches and challenges in our quest for ever faster and more reliable electronics. And as we push the limits of signal speed and data rates, squeezing every last ounce of performance out of our circuits, jitter becomes an increasingly formidable adversary. It's like trying to keep those dancers perfectly in sync while they're performing increasingly complex and rapid movements. The margin for error shrinks with every increase in speed and complexity. Jitter isn't just one monolithic entity. It comes in various flavors, each with its unique characteristics and origins. One common type is random jitter, which, as the name suggests, is unpredictable and has no discernible pattern. Think of it like the random jostling of a crowded subway car. It's always there to some degree, a background hum of uncertainty that we can't entirely eliminate. Then there's deterministic jitter, which, unlike its random counterpart, has a specific cause and often exhibits a repeatable pattern. This type of jitter might be caused by things like crosstalk from nearby signals, power supply noise, or even imperfections in the manufacturing process of the electronic components themselves. It's like those annoying vibrations you get in a car at a specific speed. You can often trace them back to a specific mechanical resonance or imbalance. And then there's data-dependent jitter, a particularly sneaky form that depends on the actual data being transmitted. This can occur because different data patterns create different electrical loads on the transmission line, leading to variations in signal propagation time. It's like trying to have that phone conversation while someone's constantly adjusting the volume on their end. The clarity of the message fluctuates depending on the loudness of the background noise, regardless of its source or characteristics. Jitter can have a significant impact on the performance and reliability of our digital systems. In some cases, it might manifest as occasional errors, like those drop bits in our phone conversation analogy. But in more extreme cases, excessive jitter can lead to complete system failures, like those dancers tripping over each other and bringing the entire performance to a grinding halt. In the world of signal integrity, it's not enough to just build something and hope for the best. Imagine constructing a skyscraper without first running simulations to ensure it can withstand wind loads, earthquakes, and the weight of its occupants. That would be incredibly risky, if not downright reckless. The same principle applies to designing high-speed electronic circuits. Before committing those intricate traces and components to a physical circuit board, engineers rely heavily on simulations to test their designs virtually and identify potential signal integrity issues early in the design process. Think of it like a virtual crash test for electronics. You get to see how your design performs under various stresses and strains without risking any actual damage. These simulations are carried out using specialized software tools that can model the behavior of electrical signals as they propagate through virtual representations of circuit boards and components. Engineers can input various parameters like trace geometries, material properties, and signal characteristics, and the software will churn through complex calculations to predict how those signals will behave in the real world. By analyzing the results of these simulations, engineers can identify potential problems like impedance mismatches, crosstalk, and signal reflections. They can then tweak the designs accordingly, adjusting trace widths, adding termination resistors, or rerouting signals to minimize these issues before they become real-world headaches. It's like having a crystal ball that lets you peek into the future of your design and make adjustments to avoid potential pitfalls. This iterative process of simulation, analysis, and refinement is a cornerstone of modern signal integrity engineering, allowing engineers to design faster, more reliable circuits while minimizing costly and time-consuming rework, later in the design cycle. It's like having the ability to practice your dance routine in a virtual studio, identifying and correcting any missteps before the curtain rises on opening night. Simulations are incredibly powerful, but they're not a substitute for real-world testing. Once those virtual circuits are brought to life on physical circuit boards, it's time to break out the big guns, the specialized test and measurement instruments that allow engineers to probe the inner workings of their creations and verify that those digital signals are behaving as expected. Two of the most important tools in a signal integrity engineer's arsenal are the oscilloscope and the Vector Network Analyzer, or VNA. Think of the oscilloscope as a high-speed camera for electrical signals. It allows engineers to visualize the shape of those rapidly changing voltages over time, capturing those fleeting nanoseconds of digital communication in exquisite detail. By analyzing the captured waveforms, engineers can measure critical parameters like rise time, overshoot, and ringing, providing insights into the quality and integrity of the signal transmission. The VNA, on the other hand, takes a different approach, focusing on the frequency domain rather than the time domain. It's like a spectrum analyzer for electrical signals, allowing engineers to see the frequency content of those signals and how it changes as they travel through the circuit. This is particularly useful for identifying frequency-dependent losses, impedance mismatches, and crosstalk, providing a different perspective on the challenges facing those high-speed digital pulses. But perhaps the most insightful tool in a signal integrity engineer's toolbox is the eye diagram. Imagine taking thousands, even millions, of those individual digital pulses, each representing a single one or zero, and overlaying them on top of each other. The resulting pattern, resembling a somewhat squashed human eye, provides a wealth of information about the overall quality and reliability of the signal transmission. A wide-open eye with clear separation between the ones and zeros indicates a clean, robust signal with plenty of margin for error. As signal integrity degrades due to reflections, losses, or jitter, that eye will start to close, with the ones and zeros blurring together, signaling potential problems that could lead to data errors and system malfunctions. These eye diagrams, along with the quantitative measurements provided by oscilloscopes and VNAs, are essential tools for ensuring that our digital devices can speak to each other clearly and reliably, even as we push the limits of speed and complexity in our ever-evolving technological landscape. It's like having a team of expert choreographers meticulously analyzing every movement of those digital dancers, ensuring they stay in perfect sync, even as the tempo increases and the steps become more intricate. As we've journeyed through the intricate world of signal integrity, we've uncovered the hidden language of digital electronics, those tireless ones and zeros that underpin our modern lives. We've explored the challenges of transmitting these signals at ever-increasing speeds, navigating the obstacles of impedance mismatches, battling the insidious creep of noise, and striving for the elusive perfection of perfect timing. It's a world of precision and complexity, where seemingly insignificant deviations can have significant consequences, and where engineers work tirelessly behind the scenes to ensure that our devices communicate with the clarity and reliability we've come to expect. From the simulations that allow us to test our designs virtually, to the sophisticated instruments that probe the inner workings of our circuits, signal integrity engineering is a testament to human ingenuity and our relentless pursuit of technological advancement. But it's not just about building faster phones or more powerful computers. Signal integrity underpins virtually every aspect of our increasingly digital world, from the medical devices that monitor our health to the transportation systems that connect us across vast distances. As we continue to push the boundaries of what's possible, cramming more transistors onto ever smaller chips and transmitting data at speeds that were once unimaginable, the importance of signal integrity will only continue to grow. It's a field that will continue to challenge and inspire engineers for generations to come, as we strive to keep those digital signals clean, clear, and flowing smoothly through the intricate circuits that power our modern lives.